Good morning. All right, it's 8 o'clock. Hopefully you can hear me. Can I have some indication that somebody hears me? Gibbs, you need to enable your video, please. Can I have some indication somebody hears me? Here we go. Thank you. Somebody's giving me something. Good. Thank you, Cade. All right. I sent you an email yesterday. I had forgotten that I had actually done the lessons that I didn't do last semester, and I actually put them up as Zoom videos. I wish I'd thought about doing that last week, but I didn't. But now they're up there, so if you want to watch them, you can watch them. Let's see. So what are we doing? Well, okay, introduction to electrode potentials and electrochemical cells. All right, so we'll start there. You don't have to go watch those Zooms, but they might be handy to you to watch them. If you watch the other videos, you shouldn't have to watch them, but if you want to watch those Zoom videos, you can. They're the same thing as I would have done last week. All right, let's get started here. Let's see, paintbrush. There we go. Okay. All right, so we'll start here on the electrochemical cells, and I'll give a quick introduction. And we'll see where we go from there. I will go back over this stuff here, the Gibbs free energy stuff, towards the end, just in the context of how they're going to appear on the test, but they're not that difficult. None of these things are that difficult. And remember that for each of these tests, there's a video for each test question. So if you're worried about the wording or how to do the questions in the context that they're presented to you, you should watch the videos to get some sort of idea about that. Obviously, the videos won't help you so much get the material, but they will show you how to answer the problems and how to interpret the wording, which is really the entire point of the videos that I give. All right, so we're going to be starting here with the electrochemical cells. Increase this in size a bit. So this is the same kind of situations we talk about with batteries and the technology involved that makes batteries work. And these are just really, the batteries are just extensions of what you're going to be learning about here. When I talk about batteries, I'm just talking about regular batteries that you put in things to make them run. So when we're looking at an electrochemical cell, it consists of these electrodes. In this case, we've got zinc and we've got copper, and these are in solutions of these specific things. Now, I need to give you a little bit of an idea. I'm going to open up this video here, Introduction to Electrochemical Cells, this one here. Hopefully you watched this one. Now, I'm not going to have any sound on this, so don't fret, but it doesn't matter because I just want to show you something here. And what it does is it goes through the difference between, here we go, the difference between ion or an aqueous solution and a solid. So we've got the zinc electrode, which is a solid, and zinc looks like this. It's a a silver metallic material. Zinc 2 plus is a solution. It's actually something dissolved in water, and you can see it's a clear colorless solution. Copper 2 plus is a blue solution, but it's again in water, and that's because it's an ion. And then you've got copper solid, which is this copper colored solid, which is different from the copper 2 plus solution. So I really want you to be aware of the difference between an aqueous solution and a solid. Does anybody have any questions so far? Okay. Now, see, zinc is in a solution of zinc 2 plus, which I've already explained how you know the difference between those two, and the copper is in a solution of copper 2 plus. Now, the other thing that we have here is a wire that connects the two electrodes, and this is what the electrons run through to go from one side of a cell to the other, and these electrons can do electrical work. So in the context of a battery, this is the electrons actually coming out of the battery to run something. One other thing, excuse me, one other thing we see here is something called a salt bridge. Electrons are negatively charged, right? And they're going to run from one side of the cell to the other. But what that means is that along with the copper 2 plus, we have nitrate ions, or no, in this case, actually sulfate ions, SO42 minus ions. And with the zinc 2 plus, we also have SO42 minus ions. But because electrons are running from the zinc over here towards the copper, that means that we need negative charges that are part of the solution here to run through what's called a salt bridge onto the other side. And this will help to equalize or neutralize the charge. Because if we just have electrons running through this wire, that's not going to do very much for us unless we can find a way to take negative charges out of this side and put them into the other side. So the purpose of the salt bridge here is to equalize the charges. Because what happens here is that the copper, and we'll see this in the next slide, the copper is 2 plus is turning into copper solid. And you can see it's actually plating on the copper metal. So the copper 2 plus is actually turning into copper solid. The zinc, on the other hand, you can see that this is dissolving. And you can see that this zinc here has actually degraded. And that's because the zinc solid is turning into zinc 2 plus. So again, this is where you have to be really cognizant of the difference between zinc solid and aqueous zinc ions, along with the difference between copper 2 plus ions and copper solid. But because we are losing copper 2 plus and it's turning into copper, the copper 2 plus doesn't need the SO42 minus ions anymore. So the SO42 minus ions flow from this side of the solution into the other side because the zinc is turning into zinc 2 plus, and the zinc 2 plus actually needs the SO42 minus ions to balance it out. So it's necessary to have this salt bridge in place in order to make that happen. Does anybody have any questions about any of this so far? Okay. So instead of drawing out these diagrams like I have here, which would be quite time consuming, we adjust them to be these kinds of metal ion type situations where we're just showing what's happening on each side of the cell. Now the double line here represents the salt bridge. So it's the marker, or the I guess the separator of the two parts of the cell. So we'll have this cell on this side and this cell on this side. In a cell diagram, by convention, the anode is always listed first. So let's talk about what we mean by anode and cathode. So there's two situations that are occurring while we're doing the cell. One is called oxidation, the other one is reduction. In order to remember what oxidation and reduction consists of, I like to use this mnemonic. It's called oil rig. Oxidation is loss of electrons, reduction is gain of electrons. So let me talk about what I mean by loss and gain here in the context of electrons. When we're talking about zinc going to zinc 2+, it's actually zinc going to zinc 2+ plus 2 electrons. Right, so this is oxidation because electrons are lost. They're on the product side. Is anybody uncertain about what I mean by the electrons being on the product side? Anybody? When I say the electrons are on the product side, is anybody uncertain about what I mean by that? All right. I hope nobody's lying to me. On the other side, we've got copper 2+ plus 2 electrons goes to copper. As you can see, the electrons are on the reactant side. And if you understood that the electrons are on the product side of the other one, there's no reason you shouldn't understand that electrons being on the reactant side here means that electrons are being gained. So that's what I mean by oxidation is loss of electrons and reduction is gain of electrons. Now you can see here that the zinc is turning into zinc 2+ plus 2 electrons. You can see how that balances. That's 2+ and 2 minuses, which is going to be 0 and then 2 minus 2 or 2 plus -2, which is 0. On the other side here, we've got 2 plus -2, that's 0, and that equals 0 on this side as well. So now the way you can tell if something's charged is if it has a superscript or it doesn't have a superscript. So zinc 2+ we know is charged because it's got the 2+ up here. But if zinc doesn't have anything up here, we're assuming the charge is 0, and that's important as well. Does anybody have any questions? Now, the other thing is that oxidation occurs at the anode. Now, the anode and the cathode are these two electrodes here. The bits of metal that are actually stuck in the solution. They're the poles of the battery, if you will, you know, the plus and minus. The things that actually will lead to the flow of electrons. So the top and the bottom of the battery are called the poles, and one is the anode and one is the cathode. Now, the oxidation occurs at the anode, and you'll notice that both O and A are vowels. So that helps you remember that. And reduction occurs at the cathode. Now, when we're talking about these, again, we're just talking about the metals, bits of metal stuck in the solution here. And you'll see that R and C, these are both consonants. So that's how you can remember that oxidation occurs at the anode and reduction occurs at the cathode. Does anybody have any questions so far? Now, so in a cell diagram, we always list the anode first. And if you look at the two things that I have here, the two reactions, you can see the zinc is losing electrons. So this is oxidation, which makes this the anode. And on the other one, the copper is gaining electrons, so that's reduction, which makes that the cathode. So in the cell diagram, we don't list water, we don't list the electrons or anything else. All we list are the things that are actually involved in the reaction. So the zinc and the zinc 2+, and then we have the salt bridge here, the double line, which is going on the other side. We're going to have copper 2+ and copper, and that's all we list. Now, how is that useful to us? Well, the thing is, we also have at our disposal something called a standard reduction electrode potential table, and you have access to this as well. Let's go back to that. Okay, standard electrode reduction potential table. Now we'll find this in the test 3 folder. And there we are. This is the table. I'll download it here. Okay. Now I introduced these tables to you in the videos from last week, but also included in these tables are the electrode reduction potentials. Now you'll notice that every single last one of these reactions is a reduction. And the reason we know that, and it even says that here, it says reduction half reaction, that's important, is because all the electrons are always on the reactant side. So all of these are gaining electrons. These are half reactions. So the implication is if these are half reactions, then 2 of them must make up a full reaction. Now here they're all written as reductions. Now how do you turn one of these into an oxidation? Well, it's pretty easy. You just flip it around. But when you flip it around, you have to change the sign that's given to you here. All right, so let's go back to here. So if we're looking at the tables here, we're only going to find one reaction that involves both zinc and zinc 2+, and you'll find it right here. That's the reaction we're actually talking about. And it has a potential, a voltage of minus 0.763 volts. And this is what we're looking at here. We call this the E0, or the electrode potential. So that's where I get this from. Zinc 2+ plus 2 electrons gives minus 0.763 volts. And the copper 2+ plus 2 electrons gives copper, and that's 0.340 volts. And we'll find that reaction here. There it is. So you'll notice that these are both written as reductions, as I said earlier. And what we know, though, is by convention, the first things that are on the left-hand side of the cell diagram here, the very first things we see, represent the anode. But what I had told you earlier is that with the anode, that's where oxidation is occurring. These are not written as oxidations, they're written as reductions. So what I need to do is I need to flip this and turn it into an oxidation. So if I flip it, the rule is that I have to change the sign of the voltage. So if it is, in this case, minus 0.763 volts, that turns it into positive 0.763 volts. The other rule here has to do with what we do with the other reactions if the electrons are not equal. Now, we can multiply the reactions, but when we multiply the reactions, we do not, I repeat, we do not multiply the voltage. And the reason for this is because voltage is what's called an intrinsic property. Now, I'm going to take this back a little bit to, say, intro to chemistry or general chemistry. Hopefully you had dealt with this terminology before, the difference between an intrinsic and extrinsic property. An intrinsic property is one where it doesn't depend on it's a property that doesn't depend on how much you have of something. An extrinsic property is one where it depends on how much you have. Now, I'll give you some good examples of extrinsic properties. That's the opposite. Examples of extrinsic properties include volume. So if you've got different volumes of, say, a liquid, then that would be an extrinsic property, because that depends on how much you have. So 1 liter looks different to 2 liters, for example. If you've got, we're talking about length of something, 2 meters versus 1 meter, clearly that changes what you have. So things like length, volume, those are all going to be things that will be extrinsic property, but they're going to depend on the amount you actually have. Now, intrinsic properties are ones that don't change based on the amount you have. One of the easiest ones I can describe here is color. See, if you've got a kilogram of copper sulfate, it's blue. If you've got half a kilogram of copper sulfate, it's still blue. That makes color an intrinsic property. Another one is melting point and boiling point. If you've got a kilogram of copper sulfate, it melts at the same temperature as half a kilogram of copper sulfate. So that's what I'm saying. An intrinsic property doesn't depend on the amount you have. Now, voltage is one of these kinds of properties as well. It doesn't matter how much you've got. And I can actually prove this to you. I think you've all seen, let me see, I'm going to see if I can find some pictures of different kinds of batteries. Let's see if I can see some pictures of these. Let's see. List of battery sizes. All right, that'll work. All right, this is cool. All right, so let's just focus. Don't worry about this 4.5 volt puppy here, or the 9 volt here. We're only interested in these. We're only interested in these 4 here: the AAA, the AA, the C, and the D. What do you notice? What do they all have in common? Well, if you look at the voltage, they all have 1.5 volts as their voltage. So as you can see, the size of these batteries is not important. They all produce 1.5 volts. Why is that? Because they all use the same chemical process to produce the electrons. Every last one of these, the AAA, the AA, and the C and the D, all use the same process. Now, back in my youth, I had this device called a boombox. I don't know if anybody knows what a boombox is. Does anybody know what a boombox is? Anybody ever heard of a boombox? Let's see if I can bring a picture of a boombox up. Let's see. I don't know. You have one, Kate. Well, that's beautiful. Let's have a look. Oh, there we go. Oh, yeah, that's old school, all right. Check that out. The thing is, a lot of you have never even seen something like this, I'm sure, but let's have a look. Oh, look at that. Oh, it's a thing of beauty, isn't it? It's got this little cassette player. I don't know if you know what a cassette is, but it's something that you used to be able to put music on, and it would play music. Interesting, isn't it? But anyways, this thing took D batteries. That's the whole point. This thing took D batteries. But if you wanted to, if you're really desperate to listen to your music, you didn't have to use D batteries. You could actually use a AA battery if you wanted to. Just stick that in instead. The only downside is that it would run out probably in about 10 minutes, as opposed to a D, which might last a couple of hours. So the only difference there is just how much of the chemical there is, but the size of the battery didn't affect the voltage that we're getting from the battery. So that makes voltage an intrinsic property. Remember, intrinsic properties only depend on how much you have. Does anybody have any questions? Okay. Well, I hope you learned something from that. You might have seen a boombox for the very first time, which I think is pretty amazing. Okay. So when we're looking at how to deal with this, we have to flip the zinc equation since it's undergoing oxidation. And how do we know that? Because by convention, whenever we're dealing with these cell diagrams, the first one listed is always going to be an oxidation, which means that once we find the reaction on the reduction potential table, we automatically flip it. And when we flip it, we flip the sign. And that's what I've done here. So it becomes zinc goes to zinc 2 plus 2 electrons. That's actually now an oxidation, and that becomes positive 0.763 volts. Then we've got the other side, which we don't flip at all because it is a reduction and it stays a reduction. Then when we add the reactions together, you can see the electrons cancel out and we end up getting the entire reaction here, along with a cell voltage. And this cell voltage is actually what we observe or should observe coming out of this cell, which in this case is positive 1.1303 volts. And this is called the cell potential. Does anybody have any questions so far? Okay. Now from this, it's also possible to find our friend delta G naught, or the Gibbs free energy, which was something I would have introduced to you last week if you hopefully you watched the videos about this. But the way that we can get to delta G naught from this kind of reaction is by this process here. Now, N is the number of electrons exchanged in the balanced reaction. In this case, it's 2 electrons. So the zinc is giving up 2 electrons, and the copper is accepting those very same 2 electrons. So these electrons here are the same as these electrons here. So what that means is that the 2 electrons are being given up by the zinc and then gained by the copper 2 plus. And that means 2 electrons are actually being exchanged in the process. So that's the N value. The F value is a constant. It's called the Faraday constant and has the value 96485 joules per volt per mole. That's a constant value. The E naught cell is the cell voltage. And then if we want to convert this into kilojoules, then we can multiply by 1 kilojoule over 1,000 joules. And this would give us the delta G naught for this actual reaction. So that's a way that we can find a delta G naught if we have an electrochemical cell. Does anybody have any questions so far? Okay. So here's another example here. And what we're trying to do here is find E naught cell, delta G naught, and K for a following standard cell. Now, when I say standard cell, what I'm talking about here are these are all set up for standard cells, and standard cells have certain characteristics. All the solutions are 1 molar, the pressures are all 1 atmosphere, and the temperature is a constant 25 degrees. So nothing else has changed. You see this says standard electrode reduction potentials at 25 degrees Celsius. The temperature will have an effect on the voltage, so it's necessary to specify the temperature at which we're taking these. But these are all standard electrode potentials, meaning it's assumed that these are all 1 molar and 1 atmosphere solutions. Now, we will look at situations that aren't 1 molar in a little while. But for now, we're just going to work with what we have here. So as I had talked about earlier, we have our cell diagram here, and you'll notice that we have copper 2 plus and copper here. So that is going to be the anode. That must mean that oxidation is going to be occurring on this side. So what we do is we hunt down the reaction, the copper reaction, which we did earlier, and that's this one here, the one that involves copper 2 plus and copper. There is only one reaction that involves copper 2 plus and copper, and that's this one. There is another one here that involves copper 1 plus and copper, but clearly that's not what we're looking for. We're looking for the one that involves copper 2 plus and copper. So what I do is I hunt down that reaction, I find it, and because it's listed first, I flip it. So the copper goes to copper 2 plus 2 electrons, and then I flip the sign on the E naught. And that's what I've done here. Does anybody have any questions so far? That becomes the first half reaction. In the other half reaction, I've got to find something that involves H2SO3, sulfur, and H3O+. Now you'll also notice there's this platinum here as well. The reason the platinum is here is because we need something to transfer the electrons. There's nothing here that is actually an electron transfer agent. These are all insulators. They are not capable of actually conducting electricity through a wire. So what we do is we stick a platinum wire in, and the reason we use platinum is because it's pretty inert. It's the same reason that wedding rings and things are made of gold, is because the gold doesn't tend to react with very much. Platinum is the same, and so a lot of jewelry these days is also made of platinum. So platinum is not very reactive with anything, which means it's not going to interact with anything else in the solution. All it's going to do is transfer the electrons. The bottom line is, if you see platinum, you just ignore it. Right? See platinum, you just ignore it because it's just there as an electron transfer agent. So what we do is we have to find a reaction here that involves H2SO3, sulfur solid, and H3O+. So I go and I look for that. And there it is there. We've got H2SO3 aqueous. We've got the sulfur solid, and then we've got H plus here. Now I want you to remember, as we had talked about with test 2, whenever you see H plus or you see H3O plus, they're really the same thing. So they work interchangeably. So all I have to do now is copy this entire reaction along with its E naught, and I just leave it go as it is because it's going to be a reduction process. And these are all reductions anyway. So I just take this reaction as it appeared on the table and just copy it down. That's my second half reaction. Does anybody have any questions so far? Now you can see that the electrons here don't balance out. And we already had stated that electrons that were given away by something in the oxidation were the ones that were going to be received in the reduction. But they don't even out. Now, so what we have to do is multiply the reaction by something, or this top reaction by something, in order to make the electrons equal. So what we do is we multiply the entire top reaction by 2, which means putting a 2 in front of everything. So that puts a 2 in front of the copper, 2 in front of the copper 2 plus, and then that makes that 4 electrons. And that makes it even with the electrons on the bottom. So now we're giving away 4 electrons, and now we're receiving 4 electrons on the bottom. What you'll notice, though, is that in so doing, I don't multiply the E naught. We talked about this earlier. E naught, or cell potential, is an intrinsic property, which means it doesn't depend on the amount we have. So multiplying this doesn't affect the E naught. You'll notice it stays the same. We can still go ahead, though, and do the entire reaction here. And you see we just bring everything down, and we end up getting the entire reaction where the electrons end up canceling out. Does anybody have any questions? So we add the E naughts together here, the negative 0.340 for the top and the 0.449 for the bottom, and we end up getting the E naught cell value that you see down here. Any questions? Okay. So the question here was to find the E naught cell, which we've already done, delta G naught and K. Now delta G naught is going to be NF E naught cell. Now N is the number of electrons transferred in the balanced reaction. That's the key word there, is balanced. So we have 4 electrons given, 4 electrons received. So N is equal to 4. The F is the Faraday constant, and the E naught cell is what we calculated here by adding the 2 E naughts together from the half reactions. and that produces some, you can convert that into kilojoules by doing 1 kilojoule times 1 kilojoule over 1,000 joules, which produces this many kilojoules per mole. So that would be the delta G naught. The K can be calculated, and again, we looked at this, or hopefully you looked at the video from last week. The K is going to be calculated by doing the inverse natural log of negative delta G naught over RT. The delta G naught is calculated from the previous line up here where we've got the delta G naught. The R is a constant, 8.314 joules per mole per Kelvin, and the temperature was 25 degrees Celsius, which converts into 298 K. When we do the math on this, we end up getting the K of 2.40 times 10 to the 7th. There's no unit on this. You'll notice everything cancels out here. Does anybody have any questions? So in summary, we can look at the values that we're getting for each of these, and we can figure out whether we're getting a spontaneous or a non-spontaneous reaction. Again, hopefully you did watch the videos from last week and got some background on what I meant by spontaneous and non-spontaneous processes. If you didn't watch the videos, then it's not something I really want to go back over at this point. You're kind of on your own with that. I really want you to either watch those videos or watch the Zoom sessions that I put up yesterday that would match the same ones as I would have given last week. But if you didn't do it, well, that's on you.
I have a question.
Yes, Alexandra.
Is K always 298?
K?
Like the K at the bottom, like the Kelvin temperature?
Well, if we're talking about 25 degrees, yes. If it's standard conditions, it's always going to be 25 degrees, which is 298 K. That's the temperature. It'll always be the temperature. The R value is a constant value too, Alexandra. The 8.314 joules per mole per Kelvin.
Okay, thank you.
Okay. So for spontaneous processes, delta G is negative. That means it's less than 0. K is going to have a value of greater than 1. And the E naught cell will be positive, greater than 0. For non-spontaneous reactions, delta G will be positive. That'll be greater than 0. K will have a value that lies somewhere between 0 and 1. And the E naught cell will be negative or less than 0. So those are just things to watch out for that will enable you to determine whether a reaction is spontaneous or non-spontaneous. All right, does anybody have any questions so far? All right, well, let's get into the non-standard cells. Now, the cells we've talked about thus far, this cell diagram, it does say for the following standard cell. And as we notice on this table here, the standard electrode potentials were at 25 degrees Celsius. So that's part of the standard cell type situation. And that also means that the solutions here were 1 molar and 1 atmosphere if we're talking about gases. So 1 molar solutions, 1 atmosphere pressures for gases. Now, what about a situation where we don't have 1 molar solutions or 1 atmosphere pressures? What do we do with those kinds of situations? Well, what we need to do is we use an equation called the Nernst equation, which enables us to adjust the cell potential we get for the standard cell with something that will take into account those different concentrations. So you can see that E cell, you'll notice there's no naught here. The naught indicates a standard cell. So the E cell here means that there's no naught, which means we are looking at the cell potential. And then that's going to be E naught cell minus 0.0592 volts divided by N, where N is the number of electrons transferred, times the log of Q. And Q is the reaction quotient. And we dealt with the reaction quotient back in test 1. if you remember what the reaction quotient was, it was like the equilibrium constant, except that it was taken when the reaction was not at equilibrium. And we'll go through how we use Q here in the Nernst equation. So this is the question that we're presented with. It's a cell diagram, but you'll notice that the difference between this and the standard cell diagram we looked at earlier is that we have these concentrations that are put next to anything that's in aqueous solution. You'll notice there's nothing next to the solids, there's nothing next to the water, there's no water here, but anything that's an ion that's subject to having a concentration here has a concentration listed next to it. And you'll notice these concentrations, some of them are not 1 molar, which makes this a non-standard cell. So it's the same kind of situation as we had earlier, and we see the platinum here. Remember, we just ignored the platinum. Does anybody have any questions so far? Okay, so how do we deal with this? Well, the first thing we do is we still need to figure out what the standard cell potential is. We need to find the E0 cell. Now, in order to do that, what I do is I hunt down the reactions that are going to be listed in the actual cell diagram. So we've got copper 2 plus and copper. So I need to find a reaction involving copper 2 plus and copper, and that's this one here. We found it earlier as well. So copper 2 plus 2 electrons gives copper. It's positive 0.340 volts. This is a reduction. These are reduction half reactions. It even says it in the table. But because it's listed first, it's actually the oxidation. It's the anode. So I flip it around. So the copper goes to copper 2 plus 2 electrons, and the E0 becomes negative 0.340 volts. Does anybody have any questions so far? So if you're looking for an actual rule here, you do have one, and that is look for the reaction that involves the copper 2 plus and the copper, and then flip it. Flip the first thing you see, always, into an oxidation, and change the sign as well. And that's what you'll need to do every time when you see a cell diagram like this. Any questions? I then need to find a reaction that involves Mn2 plus, MnO4 minus, and H3O plus. And then, of course, I ignore the platinum as well. There is only one reaction that involves all of these, and that's this one here. Let's see if we can find it. Hang on, let's have a look. Oops. What are we looking for? MnO4 minus, H plus, and Mn2 plus. Mn2 plus, MnO4 minus, H plus. Okay. Now this one here, MnO4 minus, H plus, Mn2 plus, that's the one we want. There's another one up here though that looks a bit similar, MnO4 minus, H plus, MnO2, but that's different, because we're looking for the one with the Mn2 plus. So what I do is I take this entire reaction, as I see it here, and I just copy it down along with its cell potential. I don't flip this one because it's already in reduction form. So I just take that reaction completely and just stick it right here. Does anybody have any questions so far? Now, again, you'll notice that the electrons aren't equal. We have two, sorry, go on. Sorry?
That was an accident, sorry.
Okay. We have 2 electrons, we have 5 electrons. That's not equal. So we need to find a way to make those electrons equal. So what we do is we multiply the top one by 5 and the bottom one by 2. The whole point of this is to make the electrons have the same value. So if I multiply this by 5, I get 10 electrons. If I multiply the bottom one by 2, I get 10 electrons as well. So the 10 electrons will be given up by the top reaction and received by the bottom reaction. But the 5 and the 2 were necessary in order to make that balance out. Anybody have any questions? So you can see that the electrons will end up canceling because they'll both be 10. But now to balance this, and write everything down, we have 5 copper solids. We have 2 MnO4 minuses. We've got 16 H plus. That's 2 times 8. we've got 5 copper 2 pluses on the other side, 2 Mn2 pluses, and then 8 H2O on the bottom. Does anybody have any questions? All right, so now we've got the E naught, so we just add those together, and that gives us the E naught cell, which is 1.17 volts. Now this is the standard cell potential. This would be what this would be if these were all 1 molar, but they're not. There's 0.5, this one's 1, but this one's 0.5, and this one's 2.00. So, you know, we can't use this as our cell potential. We're looking for E cell, not E naught cell. But we still need to define E naught cell in order to use the Nernst equation, which is up here. See, it involves E naught cell. It's kind of an adjuster that we add to this. Does anybody have any questions so far? Now to calculate Q, what we do is we do the same thing as we did back in test 1, where we put products over the reactants, and we put the products to the power of the coefficients. So we'll have Cu2 plus to the 5th, Mn2 plus to the square, right? Because we've got the 5 and the 2 here. That's on the product side. We've got H plus to the power of 16 and MnO4 minus to the power of 2. You'll notice that solids and water are ignored, and that's because the solids don't have any concentration associated with them, and the water is going to be the solvent anyway, and that's not really going to change. So the Q value only involves what we have for the ions. Now, another reason or another thing that we can use to make sure we only have the correct things in the Q expression is we can go back to the initial problem, and you'll notice that the only things that are involved in the Q expression here are the things that have concentrations listed next to them. So copper 2 plus, Mn2 plus, MnO4 minus, and H plus. Those are the only things listed down here in the Q expression. At that point, it's just plug and chug, and we're just plugging in the values that we had in the initial problem in order to find the Q value. Does anybody have any questions about the Q calculation? It's probably the hardest thing there. Any questions so far? Any questions? Nobody has any questions. So either you all understand or you're all lost. I'm not sure which it is at this point. All right, well, let's find out. Let's see if I can find this one. Yes, here we go. All right. So I've put up a poll. Only half of you have voted so far. I'll give you another 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. So we have about half of you who have attended here today who understand what's going on, or maybe a little less than half, and everybody else is understanding about halfway. Also, I'm asking the people who understand it halfway, is there anything that I can tell you here that will help with your understanding? Anything at this point that I can do to help with your understanding to try and get you to that full area here? Okay, I think maybe after I show you some examples, that might get you, actual examples will get to that point. Okay, so we got the Q value here, which we just calculate by plugging into the calculator, and then we plug that into the Nernst equation here. We got the E naught cell value, which was here. This is the 1.17 volts for the standard cell. We've got 0.0592 volts, which is a constant, over N, and the N is 10. If you remember, that's from the 5 times 2, whatever we needed to do to get those electrons equal. that becomes the N value. 5 times 2 is 10, 2 times 5 is 10. So that's the N value there to 10. The Q value is what we calculated up here based on the entire reaction, and plugging in, of course, these concentration values that were in the initial question, and that becomes the log Q part. And then you'll see that it's not very different really from what we calculated for the E0 cell. The E0 cell was 1.17 volts. And once we factor in this other business that comes from the involvement of a log Q and everything else that's going on here, then we end up getting 1.20 volts, which is only a difference of 0.03 volts. Okay. Does anybody have any questions? Okay, before I show you another, actual real examples from the test, I'm going to show you just one other example here for an E cell. This involves a gas. You see the gas here. So NO here is a gas. And you'll notice that instead of molar, because it's a gas, it's using atmospheres. So this is the partial pressure of the NO. But what I wanted to show you was that if it's a gas and it involves a pressure, you treat it really no differently than you would a molarity or a concentration. So you'll see that once we get down to the step where we're calculating Q, you'll see that it's NO with the 2 in front of it here. So that's going to be the pressure of NO squared. So we just treat that exactly as we would a molarity. That's all I really wanted to show you with that example, was that the atmosphere would be treated exactly as a molarity would be. Does anybody have any questions about that? Okay. All right, let's take a look at the kinds of questions you're going to see that relate to this. Okay. So what I do is I actually give you some of these from the reduction potential table. 2 reactions, MnO4 minus goes to MnO2 and MnO4 minus goes to Mn2 plus. I also give you the Nernst equation down here as well. And this is in the ungraded copy of the practice test we're talking about. So all of these are set up in this context. So this is the Nernst equation problem. And I give you this business here, this X, which is some sort of imaginary kind of compound. And what I tell you is the reduction potential for X5 plus is 1.82 volts. So let me show you exactly what that means. So when I say the reduction potential for X5 plus is 1.82 volts, what I mean by that is this. X5 plus 5 electrons gives X solid. That's the reaction we're actually dealing with. And the reduction potential, it says, is positive 1.82 volts. So the E naught is equal to 1.82 volts for that reaction. So you'll notice that it's 5 plus, and I need to add as many electrons as there are charges. That's where I'm getting the 5 from. And that gives X solid, which is going to be the result of what we get when we reduce the 5 plus into the X solid. So this is actually a reduction that we're dealing with here. Does anybody have any questions? So as I said, this is
I have a
yeah.
quick question.
Yes, Alexandra.
So, you know how you always said that, I think it's what the oxidation comes first?
Yes.
Does that not apply?
No, it does apply. But
Okay.
what I'm giving you here is the reduction potential, Alexandra.
So you just make that negative since
So
it's
we flip it.
oxidation?
Yeah. That's what we're about to do. So what we do is we take this reaction and we turn it around, right? Why are we turning it around? Because of what you just said. This is listed first, so it must be the oxidation. And the E naught for that is now negative 1.82 volts. Is that okay? Is that all right, Alexandra?
Yeah, that's good.
Okay. So now what I do is I'm looking at the rest of it. I've got MnO4 minus and MnO2 and H plus. So I have to find the reaction that's relevant to that. And those are actually listed above here. And the one that's relevant is the first one. MnO4 minus goes to MnO2. So I'm going to copy that one down. MnO4 minus plus 4H plus 3 electrons gives MnO2 plus 2H2O. And the E naught for that is 1.70 volts. Now remember, this one is a reduction and it stays a reduction because it's listed second. Oxidation is first, the reduction is second, anode and cathode. Oxidation at the anode, reduction at the cathode. All right, I'm going to stop here for a second. Does anybody have any questions about where I'm getting any of this stuff from at this point? All right, I'm going to do that poll again. Okay, so when I say topic at this point, I'm talking about just this question, okay? So I'm going to relaunch this. So just the question, not the whole topic, just this question. Can you please answer the poll here? Okay. So there's still a number of you who only understand this partially. So what I want to ask is, what is it that's confusing you? For those people who are sort of halfway here, can somebody give me some clue as to what's confusing you?
I was just wondering where you got the 1.7 from.
It's listed right up here. Do you see that?
Oh, okay.
Right,
Yes, thank you.
next to the actual reaction.
Okay.
All right. Does that bring you to full understanding, Anna?
Yes. Yes.
Okay. Anybody else who was at halfway who'd like to ask a question to bring you to the full way here, understanding of what we're doing? Well, if you don't tell me, you don't ask me, I don't know how I can do this. I've tried to be as clear as possible, but you know, if I'm not being clear, you have to tell me. Not a mind reader.
Why was it the first equation and not the second one?
Could you and then what are you asking about, Alexis, exactly when you say first and second equation?
The one with the 1.70 volts and the one with the 1.51 volts.
Oh, okay. If you look at what we're after in the problem, we've got MnO4 minus, we've got MnO2 and H plus. And we need to use the one that contains exactly what we want, Alexis. So we've got MnO4 minus, we've got H plus and MnO2. The other one has Mn2 plus. You see that? That's the difference.
Okay, I got it now.
Okay, good. Anybody else? Anybody else who was at halfway who'd like a little bit more? All right, then I'll ask again. I will ask again just to see. Relaunch. Okay, I've got the poll up again. And you see, there we go. So pretty much well, it looks like everybody understands. So there we go. That's nice. Okay, good. So we'll move on and we will see what we need to do next with this. So at this point, we've got these two reactions. You'll notice the electrons aren't equal, right? We've got 5 electrons, we've got 3 electrons. So what I'm going to have to do here is multiply this top one by 3, and I'll multiply the bottom one by 5. Now, why am I doing that? We've got 5 electrons and we've got 3 electrons. And what that means is they don't even out. So how do I get them to even out? Well, I need to multiply both of these reactions by something in order to make the electrons the same. So I do that by multiplying the top one by 3 and the bottom one by 5. Does anybody have any questions about this so far? Okay. So that would be, if I actually, what I'll do is I will actually write this out completely. It'll be 3x gives 3x5 plus 15 electrons. Now remember, I don't touch the electrode potential. It's still negative 1.82 volts. And on the bottom one, I multiply that one by 5. Notice how I just multiply all of these coefficients. Does anybody have any questions? Notice I didn't change the voltage there either. I left it as 1.70. All right, so this allows me to come up with the final reaction here, which is 5 MnO4 minus plus 20H plus. Actually, let me plus 3x gives 3x5 plus 5 MnO2 plus what have we got, 10H2O. And you'll notice that the electrons will cancel here. And then we can add these voltages together, and I'm going to get negative 0.12 volts. So the result that you get from this E0 or an E0 cell may be positive or it may be negative. If it's negative, it just means that it's not spontaneous as a standard cell. It could be made spontaneous by it being a non-standard cell. It may or may not work. We'll see, but it could be a positive or a negative value that we get here. Does anybody have any questions so far? All right, well, let's run the poll again and we'll see. Okay, so up to this point, we'll see where we're at. Give me another 5 seconds. 5, 4, 3, 2, 1. So some people aren't answering, but I don't know why. But the people who did answer seem to understand what's going on. All right, some people might be afraid not to, might be afraid to. Just remember, it's an anonymous poll. I have no clue who's doing what here. All right, does anybody have any questions? Any questions at all?
For the 7.82 volts.
7.82.
Oh, sorry, never mind. That's
It's
a
negative.
negative.
It's
I was
negative.
like, where did that come from? Okay.
So it's negative 1.82 volts, right?
Okay. Thank you.
All right. Okay. Any other questions? Okay. So let me bring up another window. No. Let's see, file, new window. Okay. So what I want to do here is I want to use this reaction to figure out the Q value. So let's see how we get the Q value here. All right. Okay. Now the Q is going to be, now it's products over reactants, so it's going to be X5 plus to the power of 3. And we got, now the MnO2 isn't going to count. The MnO4 minus, and that's going to be to the power of 5. The H plus, and that's to the power of 20. And the X isn't going to count. So look at the initial question, and we'll make sure that we've only got what we need in here. And you'll see that the X5 plus has a concentration value, the MnO4 minus has a concentration value, and the H plus has a concentration value. Those are the only things that do. So we know we're on the right track here with the Q value. So now I can just plug that in. Does anybody have any questions about how I'm getting the Q expression? Anybody miss anything there? All right, so now I can plug everything in. We've got 1.34 cubed over 1.36 to the 5th and 1.36 to the 20th. Now those values are given in the question. You see them next to the different values in the cell diagram. Okay, let's go ahead and do some math here. And I'll use this one here. That's to the power of 3. And I'll divide that by, and I'll put that 1.36 to the 5th. And then divided by 1.36 to the 20th. Oops. I'm going to have to clear that somehow. I'm just going to do a little trick here. Just ignore this. Just to fix my error here. Okay, so that should be the correct value for Q. If you put that into your calculator, you should get the same thing. I'll do it one more time just to make sure I didn't screw it up. I'll do 1.36 to the power of 25th. Okay, I still get the same value. All right, so it's 0.0110. All right, does anybody have any questions about how I'm getting that? All right, now I apply my Nernst equation, which is listed here. and it's going to be E cell, which equals E naught cell, which is negative 0.12 volts. And that's minus 0.0592 divided by N, 592 volts divided by N, which is going to be 15. The 15 is from the electrons, what they were to make them even. And that's log to base 10 of 0.0110, not natural log. All right, does anybody have any questions? All right, so let's have a look at, let me continue with the calculation here. Oh, it went away. All right, so let's do 0.011 and 0, and to get the log to base 10, right? And then multiply that by 0.0592 and divide that by 15. So it's going to be negative 0.00.77. So the answer here will be, you'll see that's going to be plus. So it'll be negative 0.12 plus that. Okay, so I will just, actually I'll just remember that.
Question.
Yes, yes.
Where did you get the 0.0592?
It's in the, do you see that? It's in the,
Oh, okay. Okay.
it's in the equation.
Okay.
All right. Okay, so let's see. So I'll just do this. So it'd be 0.12, and there's your plus minus there, and it'd be plus 0.0077. And the answer is going to come out to be 0.11, or negative 0.11. Once we take significant figures into account. So this entire thing here was negative 0.07, sorry, negative 0.0077. All right, does anybody have any questions?
I actually have one question, like if we're done for the day.
Okay, I think, well, okay, I didn't, before we do that, does anybody have any other questions about this? All right, what was your question?
So I know for test 3 we have that essay question.
Yes.
Are we going to be given that essay question and go over it before the test?
Actually, why don't we do that now? Thank you for reminding me. We'll go ahead and do that. Okay, let's take a look at the essay question. Thank you for bringing that up.
Yeah, thank you.
Okay, so the parameters for the essay question, which will be placed into a Dropbox sometime before before the due date of the test. And here it is. So the notes about the essay question, it's in the test 3 folder. There we go. And these are the topics. So there's going to be seven topics, and they're all to be 50 words each. Each essay needs to include a reaction that relates to what you wrote for the essay. So at the beginning of the test, which means before it means effectively before test 3 is due, you hand in the essays, and they must be handwritten, not from a Word document and not photocopied. Handwritten is going to be the key word here. It'll be graded out of 20 points. All essays must be completed, not just 2 of them. Be sure to include a household object I specify in the Dropbox directions. Okay, so let's have a look at what I mean by the Dropbox directions here. which I don't know if I've changed this yet. I might not have. Let's have a look. Let's see. So where's the drop box? Here it is. And let's see, I'm going to actually change this to a teaspoon. So you need to include a teaspoon in each picture. That's weird, isn't it? I've lost my mind, haven't I? Can anybody know, does anybody know why I'm asking you to include a teaspoon? Or do you think I'm just nuts?
So we can't.
You can't cheat.
You can't cheat. What do you mean by cheat? I mean, how would that prevent cheating?
So
I
it's
don't
your
know.
own picture.
Yeah, it's your own picture. That's right. Yes. That's right. So it's your own picture. That's the whole point. But you need to sign across them as well. It should say that here, hopefully. All essays need to be completed. Must be written. I think I will add that too. They need to be signed as well. So sign across each picture. And below that, I also have an example. Let's see, let's go back to the test 3, the notes about the test 3 question. I actually have an example shown here of, there we go, corrosion of iron and electrolysis of, yeah, so it gives you an idea what I'm looking for. Okay. All right, so there you go. All right, we'll leave it there, and I will talk to you all on Thursday. And bye for now. No worries, Gabriel.